Ladies and gentlemen, welcome to 6-4E and the natural logarithms. You remember your good old compound interest formula, right? A equals P times 1 plus R over N to the NT power. What do all these things mean? Well, you've got the amount in the account, after, T years. We've got the principal. Okay, got to remember this. Principal. I'm going to spell it wrong. I just know I am. Can't find any place that has it. Oh, there it is. Okay. And then we've got our interest rate as a decimal, right? Keep that in mind. It's a decimal, the decimal, not the percentage. So if it's 8%, you'd put 0.08. N, which you see twice in the formula, is the compounding factor. And T, which is years. Keep that in mind in case they decide to give you months, and then you would convert it to years. Now, let's suppose, for instance, you were bored, and you thought, hey, it would be kind of fun if I thought about investing $1, that's right, $1, at 100% interest rate, that's 100%, for 1 year. And then changing the compounding factors and see if that makes any difference. I know, you would be excited. But there was a real guy who did that. His name was Leonard Euler, spelled E-U-L-E-R. Euler, not Euler. Okay, and he decided to increase the compounding factor. Obviously, if it's a 1 compounding annually, you get $2. Right? So you'd invest $1, you get $2 back. Well, he started to increase the compounding factor, and what he found out was, for if you have a daily compounding factor, 365, you get this value. And as you increase that hourly, even to every second of the year, the number keeps getting bigger. But if you notice, it's starting to slow down. It's not increasing by the same amount each time. In fact, there's a big jump in the number of times you're doing it from hourly to every second, but not a big jump over here, which means it's slowing down. If you were to look at a function, you'd actually see it had a horizontal asymptote. I know, really super cool. And that horizontal asymptote, that thing gets closer and closer and closer and closer to, but never touches, happens to be this gargantuan number. It's irrational. It goes on forever and ever and ever. Never stops, never repeats. Okay? That number that he found, they decided to give it a cool name. E. Your calculator has E programmed into it. No, you don't need to memorize it. However, if you recognize this number, look at the sign outside my door when you come into my room next time. You will now get the joke that's on the wall outside my door. Not about the domain. It's the other one. Okay? Look for this number. Then you'll understand. Okay, the next thing we need to talk about is annual yield. Okay, annual yield is found by, it's this part of that compound interest formula, minus the original $. So this is how much you would get. Like if you invested $1, this is how much you would get after 1 year. So if you subtract off the original $, you get what's called the annual yield. So this is the original $. Now, compounded continuously. That phrase, every time you see that phrase, you are going to think E. That's what that means, compounded continuously. So take a look at the annual yield as N gets bigger and bigger and bigger, really, really super big. This thing turns into E to the R power. I know, kind of cool. So this formula that we saw before changes to P, then you got your E to the R, and your exponent t. Ah, the PERT formula, right? Because you just substituted e to the r into that place for the annual yield, or at least that portion of the annual yield kind of thing. So let's see, if I had in example 1, they talk about, well, let's say you invested $500 at an interest rate of 8%. We convert that to a decimal. What's the annual yield? Well, keep in mind, since we're compounded continuously, we are talking about e to the r minus 1. So that's e to the 0.08 minus 1. Now, handy dandy machine here. E to the 0.08 minus 1. Let's do that. E 0.083. Alright, so that's an 8.3% annual yield. It's not just 8%, because you're compounding continuously, you actually get a little bit more. Okay, so what about the value after 1 year? Well, that's the PERT formula, right? A equals $500 e to the 0.08 for 1 year. Well, we kind of already have that part, right? We just need to take our answer times 500 and find out that. Wait just a doggone second. I did something wrong there, didn't I? Let's go back and redo it. 500 e to the 0.08 times 1. I know that really won't make a difference. See how we have parentheses around our exponent? Oh, that's much better. $541.64. Example 2. Compounded continuously 4.5 years, same values for principal and interest rate. Well, it's not like this problem is changing dramatically, but you do have the additional exponent there to worry about. So, if you know how to operate your calculator, you can use the second enter feature, which brings up the previous instruction. We're going to go back to the 1, which is the year that we previously had, and change it to a 4.5. Then we can hit enter and find out that there's $716.66. Now, how does that compare to compounded quarterly? Well, compounded quarterly, when we start with $500, quarterly would be 4 times a year. So you have that 4 times 4.5 in your numerator. I don't know, let's see here. $500, 1 plus 0.08 over 4 in parentheses, raised to the parenthesis. Got to put parentheses around your exponent, otherwise you're going to mess it up. 4 times 4.5, giving us $714.12. So how does it compare? Well, it looks like you got $2.54. $2.54. Oops. Not an idiot. Okay. Next. What does this function look like? Y equals e to the x. Well, it's an exponential growth function, isn't it? How do I know that? Because e is bigger than 1, right? You know your exponential growth functions, right? The b value has to be bigger than 1 to be growth. Well, I'm pretty sure 2.718 approximately is bigger than 1. So that must mean we're in the growth category. Right? So this is approximately the same thing as something like this. Not quite, but approximately. So exponential growth functions, we know what those things look like. What's the y-intercept on this? We talked about last year how it's the value of a, and in this case the value of a is a 1. So this is the value 0, 1. What's the domain? All exponential growth functions have a domain of all reals. You remember the sign for all reals, hopefully. What about the range? Well, it looks like it's bigger than 0. Y is bigger than 0, not equal to, because we have an asymptote at y equals 0. Right? The good old x-axis. What's the inverse of that look like? Well, switch x and y. Yes. How do you solve that for y? Change it to its other form, right? What's its other form? Okay, let's see. The base, it's got to be a log, right? So let's see. The base is e. The argument is x. The exponent that it equals is y. So it'd be log base e of x. You will never ever see log base e of x on any t-shirts or billboards or advertisements or anything, right? It's not even cool to say that at parties. In fact, people are going to laugh at you if you do. Everybody and their brother is expecting you to write ln of x. No, that's not in. That's ln. Because base e logarithms are called natural logs. Logarithms, I should say. So you will always see it y equals the natural log of x. Every time you see ln of x, you know the base is e. Just like every time you see log x and there's no base, you know that it's a common logarithm, base 10. So this logarithm function looks just like all the other ones. What point is there? Right there on the x-axis. Yes, that's the point 1, 0, because all the log functions go through that point. What's the domain? Well, x has to be greater than 0. It's everything to the right of the y-axis, all up here. The range? Yes, all reals. Any asymptotes? Sure, x equals 0, right? The good old y-axis. Boy, that looks awful familiar. Since they're inverses, everything just switched. Yeah, you better understand that. Okay, so one of my favorite examples is coming up. And so I'll read it to you from the book here. Hopefully you can still see that. Tilt the book just a little bit right there. Okay. Under certain conditions, the height in feet above sea level can be approximated from the atmospheric pressure P in pounds per square inch, PSI for short, using the equation blah. There it is right there. Human blood boils at 0.9 PSI. Good to know. And such a situation is fatal. No kidding. At what height above sea level will blood boil in an unpressurized cabin? Yeah. Okay. You know, who's floating around in a log cabin anyway? I mean, seriously. Okay, so we've got this equation. The human blood boiling thing kind of is a little bit humorous, although if it was happening to me, it wouldn't be that humorous. Okay, so let's see. Pressure is 0.9. Find H. So they just want me to take the natural log of 0.9 minus the natural log of 14.7. and divide that by this nasty looking number. I'm pretty sure that you children out there are capable of typing ln.9 minus ln 14.7. Enter. Divided by negative 0.0000039. I think there's 4 zeros. Is that right? Yep. Okay. Whoa, 71,620.7. 1,620.7. Okay, that's the height above sea level that you have to be before your human blood starts boiling. So word of caution to you this weekend: try not to go up that high. I know that there are some of you with fairly large vertical leaps, but please resist the urge to do that because I want you all to come back and learn from me next week. Have a great